fashion through space. We're not quite there yet, but we're very nearly there. So just a quick review. We've taken this course quite a long way. When I was in second year, I believe this was roughly where we finished. We've covered a lot of material. Okay, there's still some more observations to cover, and then we'll finish what I did. So, let's have a quick recap. I believe that this is also important for you guys. Those of you with an oral test this week, everybody who's done the oral test will tell you the first question in the oral test is what are the most important things in the course. And it's a very important question. It'll probably be a question in your test. If you cannot identify the really important points, you haven't taken anything home. So let's go through them. We started out by reviewing Newtonian mechanics, and we looked at this system of mathematics that Newton derived so long ago and that so accurately described the way that the universe works. We looked at the laws, the idea of force, kinematics and dynamics, and we revised these things. And then I promised you, right from day one, that we were going to come up with a new scheme that would dramatically revolutionize the way that we saw mechanics, that would take the mathematics and massage it into a form that was beautiful, into a form that was elegant. And we have achieved that. How did we do so? Well, we began with Newton's laws. And we started considering systems that were constrained in some geometric way. So we more intimately considered the geometry behind physical situations. That we are confined to move inside a plane, or on the surface of a sphere, or on a hoop, or along some wire, or any other constraint manifold. Once we had defined these constraints, these so-called holonomic constraints, we needed a way to express Newton's laws so that these constraints did not figure either in their geometric constraining form or by means of the forces of constraint. So we massaged Newton's laws. We went through quite a lot of work, and what popped out, well, along the ride we came across something called the Inertia equation, and ultimately what popped out were these Lagrangian equations of motion. And what were these things? Nothing but Newton's laws. But Newton's laws revitalized, taken from their old and stagnant form and brought into a new being. These were Newton's laws, but with power. So, what power? Well, when we took the Lagrangian equations and we moved them from one coordinate system to another, they remained the same. There was something deep underlying their very nature that would not change when we changed coordinate system like Newton's laws did. Yet these were Newton's laws. What else was powerful about it? Well, when we took the Lagrangian equations and we applied them to some system in physics, we did not need, as we had set out to get to this point, and we certainly had arrived there, we did not need to consider the forces of constraint. Nor did we need to consider anything about the constraints other than that we could parameterize the surface upon which the system moved. So, the Lagrangian equations allowed us to ignore constraints. And indeed, in the naive approach to the Lagrangian equation, we didn't need to reason about the constraints at all. The tension is that force that keeps the geometry of the pendulum the way that it's supposed to be, a constant length from the origin. The normal force is that force that prevents us from falling through the plane of motion. But these forces are not forces we can reason about in the Lagrangian equations. Instead, we have a new set of equations that allows us to talk about these forces in a very powerful, allows us to talk about the rest of the system in a very powerful way, ignoring these forces in time, just looking at the geometric effect. Although there are methods of just concluding what these forces are, we have not covered them. They are called the method of indeterminate Lagrange multipliers. And some of you are doing it for your assignment. So, we then moved on. And I told you quite a while back, all right, we've now come to the city of Lagrangian mechanics, and we're going to start looking at some of the attractions. And that's what we then did. We then moved around and looked at all the different side topics that we could consider. Our first stop was conservative forces. We wanted to find something, underlying forces that can be derived from a potential function. We found 4 equivalent statements for a force to be conservative. 1, the work done by the force is independent of path. 2, the work done by the force in a closed loop is 0. 3, when the flow of the force is taken over some simply connected, if the force is defined on simply connected domain, the curl of the force will still be 0 everywhere. And 4, the definition of conservative, which was that the force is minus the gradient of some potential function. Once we characterize these potential forces, these potential functions and these conservative forces, we started to ask what they meant. And certainly in terms of the Lagrange equations, we were able to make them even more elegant, even more tunny, even more deep. And in fact, the links that these new equations that we derived have to other deep parts of physics we haven't even begun to investigate. And that's part of what we'll do in the remainder of the course. But what we came up with was this concept of a Lagrangian, which in our case was T minus U. And this guy was essentially an object that encoded every possible detail about the motion of our system. And it encoded these details completely. There was nothing not contained inside the Lagrangian. As soon as we decided on the degrees of freedom, the generalized coordinates, the kinetic and potential energy, everything else was solved. To the level that, if you get mathematical Lagrangian, mathematically you can get the Lagrange equations. Go and look on the course website. I've got a mathematical notebook that does just that. So, Lagrange's equations were algorithmic. Another point that was in their favor, especially once we defined kinetic and potential energy, it was a very step-by-step procedure to define the Lagrangian and to solve the equations in motion. This is extremely useful because it means that very complex systems can now be reasoned with using computer algebra systems like Mathematica or Sage or Maple. And this is a very good thing. It enables us to talk about things like pendulums with n links and approximating ultimately things like ropes. So it enables us to extend what we can solve before. It enables us to look at Lagrangians for which the equations of motion, if we wrote them out, would be 7, 8 pages of written equations, which would be something impossible to deal with or extremely tedious to deal with by hand. But now it's possible. So this form was central. And we had equations of force of motion in terms of this. That looked like d by dt del L by del Qi dot equals del L by del Qi. So we had now described this very general form of Lagrange equations. And we moved on with a brief nod to things like non-conservative forces, things like friction, and saying that we could just add in the component of non-conservative force. We moved on. And where did we go? Well, we went to our next stop, which was to consider systems. And this is where we still are. We're in some of the more exotic parts right now, but we started quite simple. We considered a simple system, a seesaw, a balance, and we solved it using Lagrange's equations. And someone actually came to me and said, we don't need to use Lagrange's equations here because we could just do this for talk. And it's true. You could do this in many different ways. Center of mass is in fact not a concept in Lagrangian mechanics. It's a concept in mechanics as a whole. So when we derive the center of mass, we use Lagrange's equations. I thought it would be some good practice. But in fact, you can get there in a lot of different ways. And the point that you come up with is something central. To any system, there is one point. And there are special characteristics of that point. One characteristic was gravity will act on the whole system as though it were acting on a point of the mass equal to the mass of the whole system located at the center of mass of the system. And we can get the potential energy due to gravity very simply by saying that the potential energy due to gravity is the mass of the whole system times u times the height of that special point, the center of mass. But that wasn't the only nice feature of the center of mass. Indeed, there were more. And one such feature that we may have stated about Bruce, but it is certainly proved in chapter 3's notes, is that when you apply a force to the system, and I mean a net force now, so you apply one force to one particle and one to the other, and you add all the forces up, and you ask what is the net force applied externally to the system of particles, then you'll have this rule. This total external force will move all the particles in such a way that the center of mass will move, as though it was simply this external force acting on a particle of mass m, centered at the center of mass. So the center of mass was very nice. And it enabled us to find things, to reason about things like forces, and I spoke to some groups in the oral test about what it would be like for a high jumper jumping over a pole, and how the center of mass of the high jumper it doesn't really go over the pole, it stays under the pole, although the high jumper himself manages to go over. Well, because he arches his back and then he's a semicircle and the center of mass is underneath him. And you also find that you don't lift your center of mass very much when you jump. Alright, I'll demonstrate this. I'm not an Olympic high jumper. What? I can't jump very high. I'll be honest. In fact, I suck. Look at this. Woo, this high. Well done. Right, so it's about this high that I managed to jump. I'm not an Olympic high jumper, but I am a human being. And the reasoning is, Olympic high jumpers, they are also human beings, although they're very close to the superhuman. The likelihood is, if they were to jump whilst remaining completely rigid like I did, well, they wouldn't jump this high, they'd probably jump this high. Not much higher. The center of mass is not going to lift much more than this. Well, there's a problem. You're never going to get over a pole this high by jumping like this. It's not going to happen. So you've got to redistribute your height, your mass distribution, in order that the center of mass is as low as possible relative to the rest of you. So think about it. The center of mass is here. If you can lift it up this high, someone who could jump whilst remaining rigid this high, well, they could get over a pole around this high, as long as they could make sure that this point, the center of mass, lifted this much, and the rest of them was above that. And the way you do that, you arch your back, and you go flat. Because when you're flat, your center of mass is sitting in the middle here, as opposed to in the middle here, with a whole lot of you below it. And if you can arc yourself, the center of mass is sitting even underneath that. And so you'll notice that the best high jumpers, on their best jump, will actually go over completely arced backwards, instead of just flat. Right, so there were very interesting considerations to do with this point, the center of mass. And then we moved on and started considering a new concept. Oh, and the center of mass, of course, was defined as three vector equations, RCM is 1 over n, integral sum, depending on the system is just straight or not, of, right, so there were three equations there, that's a vector equation. And then we discussed a new point, a new quantity. You see, we were interested in determining the kinetic energy of things. And we had figured that the kinetic energy of any system is the kinetic energy of the center of mass, half mvcm squared, plus some internal motion of the system around the center of mass. But now, we needed a way of reasoning about that internal motion. Right, if the system was a fluid, or if the system was a gas, there would be special ways of dealing. And that's your program for next year. But we were particularly interested in things that are solid, rigid, immovable. Well, not immovable, but not dentable. So, in considering such objects, which we call rigid bodies, we started to discuss them. And we talked about how the constraints for rigid bodies are autonomic, but they are not independent. And we came up with the fact that every rigid body has 6 degrees of freedom. We had various ways of characterizing these degrees of freedom. X, Y, Z, pitch, roll, yaw. And we asked questions of these rigid bodies, and in particular we were interested in what is the kinetic energy of a rigid body. And what we discovered was that if the rigid body is rotating about some axis, which instantaneously is always the case, we can define a quantity, which we call the moment of inertia as that rigid body is rotated about this axis. And this quantity enables us to determine the kinetic energy of the rigid body, that system of an infinite number of particles, or even a finite number, as it is rotated about that axis. And that's really it. But we're not quite done. There are a couple of loose ends. We'll tie those loose ends up today. We're going to discuss moment of inertia in a little more detail. So let's just recap. You have this statement. The moment of inertia, when we rotate the object about some axis, is given by the sum or the integral of the system. I tend to use integrals. The integral of the system of the perpendicular distance of all particles in the system to the axis A squared. Right? Unlike the center of mass, which was a vector quantity, which had three components, the moment of inertia is a scalar quantity. It has one component. Although we will soon discover that in fact the moment of inertia is much more general than that. When we don't want to specify our axis, the moment of inertia is a tensor quantity. And we'll get there today. But this is where we work. We specify an axis and we compute it, the moment of inertia. And that was great for things like a rod pendulum, which was going around the same axis the whole time. The axis was sitting through the screen, and we had some object rotating around that axis, and it was very easy. Well, what did we do? We computed the moment of inertia from this axis to every point in here. We integrated them up. We got an answer. I think it was something like 1 over 12 ml squared, where others left it out. And so we say, all right, moment of inertia here is 1 over 12 ml squared, and we could compute the kinetic energy very simply. The kinetic energy then, 1 over half I omega squared, where omega is the angular velocity of the thing around that point, the axis, which was in turn equal to a half times I over 12 ml squared, and omega, of course, is theta dot. And there we go. We can substitute in. We have general coordinate theta, and we could shove in the potential energy, of course, which was mg times the height of the center of mass, which was normally something like minus L cos. Once we had kinetic and potential energy, Lagrangian popped out, and everything was all good. It's all very well and good. But some of you who were thinking about your assignments, no doubt, started wondering, well, this is great. We're computing this around one axis. But that's not generally the case. That's not generally how things move. If I throw this duster in the air and catch the game, it doesn't just rotate around one axis. It generally rotates around many axes. It does quite a convoluted motion. So, in order to describe the motion of this duster as it flies through the air, or as it passes through a magnetic field, or as it gets pulled by gravity, or some other motion of any rigid object, we need more. We're not satisfied with simply working out how it moves when it's rotated about one single axis. Well, how do we deal with this problem? The problem, of course, is this. As we change the axis, if we change A to some other axis, the way we have it now, we have to do an integral again. And if we change it to yet another axis, we have to do another integral. So if the axis is changing the whole time, we have to do an infinite number of integrals, and that just doesn't feel like fun. So, what do we do? How do we get around this problem? And when all else fails, it's always good to write down a little bit of vector algebra in the hope that it will elucidate some of the points. That's what we're going to do now. And all of this has been written out painstakingly by me over this weekend in your notes, and I hope you appreciate it. By the way, it still stands. One person today has sent me a correction to chapter 2 notes, which was taken into account. The if you send me corrections to the notes, it's the same thing as if you make an important comment in class. I'll put your name on a list somewhere. If you're on the border of any mark, I'll push you up to that mark. So if you're like 49, I can push you to 50. If you're on 74, I can push you to 75. If I don't see your name on the list, it's too bad. Your name on the list, awesome. So someone has emailed me and their name is on the list. Someone emailed me saying, "Ooh, chapter 2 notes has an error in them." It was Richard, and he basically emailed me and said, "I'm not so sure about this line," but essentially he was saying, "Hey, guy, you made a mistake," and he was right. And the mistake has been corrected and his name is done. And it's very good. I encourage you all to do that. I mean, I sit on in 2 days and I write 60 pages. There's going to be errors in it. So search for them. Right. So, we're now going to do a little bit of formal algebraic reasoning. Just a brief check. We have hardly any lecture time, but anybody up for a 5-minute break, or do you want to press on? Press on. Yeah, I think that's wise, because I only arrived at like a little lecture here. Right, so let's draw a little diagram to understand exactly how this moment of inertia is computed around an arbitrary axis. So I'll draw the axis in now. And bear in mind that everything is three-dimensional and it's a bit hard to write down on a page, but I can make a good attempt at it. So let me draw the axis and let me call it N. Right, and let's make it a dotted line beyond this vector. N is a unit vector, let's say, the direction of the axis around which I'm rotating my object. So in this case, I've drawn N in the page, in the board, and the object will therefore be rotated around that axis. Right, so let's consider some point. We'll consider the rest of the object later, but let's just consider one point. Let's put it here. Now if I take this point around which I'm rotating stuff, say the center of mass, or any point, right? If I pivot something at a point and I let it rotate arbitrarily, then it's another point. And for instance, those of you doing a spinning top or a gyroscope. Show of hands, spinning top or gyroscope groups. Yeah, there's quite a few of you. A lot of you will be considering instances where you fix one point, the bottom of the top or the point on the gyroscope, and you let the whole object do its stuff around that point. So this is a situation like that. We're fixing a point, and we've got an axis that passes through that point, and now we want to see what happens as we rotate around that axis, even infinitesimally. So here is some position in space, and I'm going to call the vector from what I'm going to call the origin, the point at the bottom of the top, to that vector. I'm going to call that R, right? That's just a normal displacement vector. Now this guy doesn't have to be in the board. He can come out of the board. He can be anywhere, right? But the important thing is that we can project R onto the direction of the axis. We know how to project one vector onto another vector. I wish I had color choice. Right, so if we project this vector on that axis, we get this vector, the projection. Now the projection of one vector onto another, when the reference vector is of unit length, is given by what? Anyone know? Especially those of you who came to an old test on Friday, you have no excuse. The dot product. It's simply the dot product. Right? And we can derive it if you like. There's a theta there between these two vectors, right? So the length of this thing by trigonometry is very simply R cos theta. But remember that n is a unit vector, so I can multiply by 1. Wow, that thing there we know to be n dot R. Right, so the length of that projection there is simply the dot product. That's the length of the projection. What's the direction of the projection? n. So the projection itself is given by n dot r, its length, in direction n. Right, that's because n is a unit vector, so we're not dividing by n squared or anything, which we did otherwise. Right, but the projection isn't the thing we're interested in. What is the thing we're interested in? The perpendicular distance to the axis. And how do we get the perpendicular distance to the axis? Well, no other way than simply subtracting this vector minus this vector. That will give us this vector. This guy, going upwards. That's the quantity we'll care about, because that's the quantity that gives us our perp, so-called R perp. Oh. Right. And why do we care about R perp? Because when we're computing the moment of inertia, we're integrating through these things. Right, so let's consider this in algebra. What does this look like in algebra? We said R perp is given by R minus the projection. N dot R N. So we computed this thing. And now we simply want to find out what do we want to do with R perp. In the expression for moment of inertia, what do we want to do with it? We want to square it. How do you square a vector? Sharing something? Dot product is known somewhere indistinguishable. Yes, dot product. You just take the dot product of the vector with itself. So we can do that. R perp dot R perp equals R minus n dot R n dot R minus n dot R n. And we can compute this guy. So back to R dot R. Minus n dot R n dot R minus R dot n dot R n, and finally plus n dot R squared, this coefficient here, times n dot n. Right, let's control that. So that's just expanding this out. So this R dot R, we can write it as the magnitude of R squared. It's a scalar quantity. Magnitude of R squared. And this thing here is n dot R times n dot R. Well, that's just n dot R squared. And this one is R dot n times n dot R. Well, that's also n dot R squared. So we've got minus 2 n dot R squared plus n dot R squared times n dot n. What's n dot n? 1. N is a unit vector. So this is just plus n dot R squared. Right, we've got minus 2 plus 1 of the same thing. So we can write this simply as R squared minus n dot R squared. And that's great. That's an answer in terms of vectors. Have any of you ever heard of the idea of a quadratic form? Yes. The very last expression. Okay. So you mean this guy. So essentially what we're saying is the length of this vector is n dot R.